Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatan min lisani yafqahu qawli. Dear students, Assalamu alaikum. Today I will discuss another topic on scheduling technique for highway construction project. The topic that I'm going to discuss today is LOB method, and as you all know that I am Professor Adnan Qadir. Now, what happening here mainly that many of the highway projects are in linear in nature. So people think that this is LOB method, or we call this as a line of balance method, is a most appropriate method to represent, to schedule techniques for your highway construction project. This method is also called repetitive in nature. It is executed by a series of operations which are repeated in part or section of the project. Actually, for highway, when we deal with the construction of same new project, the same operations like clearing and grubbing, placing the sub-base, the base, the asphalt courses has to be repeated many a times. So that's why it's good to use this technique, the line of balance method. So let's start elaborating what is LOB method, and this content of this lecture also shows you the solved example. Now, let's go with this. Now, as I said, LOB means the line of balance. It is also known as the repetitive scheduling method. The main purpose is to ensure that many activities of repetitive production stay in balance. It allows an even flow of items produced through a process and a speed compatible with the goals set forth in a plan. This repetitive work can be shown as a single line on a graph. Line, there are x to xy actually graph. One line represents the operations. The slope of the line indicates the rate of operations. And as I said, the projects that are linear in nature, like pipelines, tunnels, rail tracks, and shoulder improvements, are the example of this method. So what is the advantage, as you will know in a little while, that it clearly shows the amount of work taking place in a certain area at a specific time of the project, has the ability to show and optimize the resources used for a large number of repeated activities executed in several zones or locations. It's easier cost and time optimization analysis because of all the information available for each activity in the project. It has a superior presentation and visualization. You can modify, update, and change the schedule. You can also manage various subcontractors in the projects. It also allows for simpler and clearer resource management and resource optimization functions. And it can help you visualization of the productivity and location of the crews. And it can also help the manager, the, the site manager or the site head in the middle of the project, whether they can meet the schedule if they continue working as they have been till now. LOB has certain constraints, like under circumstances, you can two operations overlap, then this may not be a very good representation of the thing. And this is a main constraint. That is for example, the asphalt concrete cannot be laid without the base, and the base cannot be laid in one layer depending upon the thickness of the base. So every activity has to follow the activity. It's not like, in a building project when you can do certain things in parallel. This is one of the constraints. The user has to establish a minimum interval of time or space between the start of an operation and the start of the operation that is following it. So this is the problem where a contractor faced that he cannot execute two operations on the same location at the same time. So you can also cite an example that if a contractor wishes to determine when to start the base after starting the sub-base in a specified location. So this is a buffer time that is needed. Then there is a limitation. If the project is not a pure linear project, for example, in a rural highway construction, yes, you have a linear thing like that. But when you are working in an urban environment, then there's a problem that there are utilities, there are a lot of obstacles, traffic diversions. Traffic diversion also there in rural highways. But for working in the urban limits, it has own dynamism, and you cannot do the project in a pure linear manner. So this is the problem with this method or this limitation. And that's why it is not as common as the other method like CPM and PERT in construction project. And people try to adopt the same thing, the same PERT technique in highways as well. So that's what not feasible when flow of work is obstructed due to utilities or relocation, etc. This method is obviously it's not very popular, though in the recent decade people have started focusing in this method. Now this method is represented by a diagram, and it can have many shapes like the one show that there are three activities. We have number of units. These number of units may be road kilometers, we can say, and this on the y-axis duration. Now, while I am explaining LOB in the context of highway construction, I did not want to say that it cannot be used for building construction project. Yes, it can be used in a building construction project. So that's why this, though our focus of this lecture is on highway construction, but this can be used. That's why this number, the number of units can be in houses as well. But our focus is highway, so we can take this y-axis as the route kilometers that have been been asked to be constructed. And now you can see three boxes, three bar charts that are inclined, and in between those bar chart there is a minimum buffers as explained. Now, if you can see, look at the slope. The flatter the slope, the gentle the slope, it means the activity is slower, and the steeper the slope, it means the activity is fast. So we can see from this graph that with a non-parallel working, the rate at which A has been completed is more efficient than the rate at which B and C is to be completed. Or we can say the the activity C is more slower than activity B and A just by looking at this graph. And this, now you can see that within this 5.5 kilometers, we can see in segments that what's happening in the project, why our project is deviating away from its normal scheduled time. So that's where we can you start investigating and start looking at the faults that have come along. Another diagram is, now this is an ideal diagram in which the rates are equal, and you can see as evident from the graph, all graphs are parallel and they have the same slope. Now this is the thing that operation B and C has a beginning together. So this can also be shown in a level graph, but people don't admire this type of thing because normally it doesn't happen in a highway construction project. But this is the problem with us as like a highway engineer. We tend to forget that within a highway project, the construction of a bridge or culvert is also a part of highway project. So that's why if you can have, say, a highway project starting with the construction of road, and in between that segment of a road there is a bridge, so we can start that activities also as parallel, because that activity is totally different. It is not dependent on activity B. So this is one example. And likewise, B and C can be completed at the same time. But the restraint would be that in no circumstances C can be completed earlier than the B. So this is a point that is to be noted, and inshallah, this is being explained in the solved problem that we are going to do it after this slide, as I guess. So let's see the example problem on LOB data of highway projects. This example is purely hypothetical. It may have values, they not be very specific. It's just for explanation of the problem. Some data has been exaggerated, but obviously the main purpose of this presentation to explain the LOB data, how you use LOB technique for scheduling your project. So let's see that we have the given data, activity description, labor hour per activity, minimum buffer time, and operation per activity that is given to us. We have 5 activities: clearing and grubbing, earth moving, sub base, and asphalt paving. There is a requirement of the project that the total length is 6 kilometers and we have to complete 1 kilometer per week. This is the rate that has been asked to us by your client. And this length of the day is 8 hours and it's a 5-day working project. Normally, in countries like Pakistan, we start this project. We have 7 uh, weekdays, and sometimes we work in 12 hours per day in shift. So, but again, this whatever I'm saying is that these all things are variable, and my data, this example is more of a general data than a specific road data. Now, how to do this, the solution steps. So in order, obviously we need to have the objective is to have an LOB diagram. But for LOB diagram, we have to have the following output. We need to know what is the theoretical gang size. Once we know theoretical gang size, we can know the actual gang size. We need to calculate the rate of output. And we need to know the time in days of one activities. That is time from start of one unit to start on last unit. The start day of unit 1, end day for unit 1, start last unit and finish last unit. What I mean, for example, we have 6 kilometers of the road here. So we will need to know, I'm talking about this thing, when the first kilometer will start, when it will end, and simultaneously what is the starting time, what is the duration that will be needed, maybe the starting time that will be needed for the 6th kilometer or the last unit that is been given, and the finish time of 6th kilometer of that particular activity. So we will calculate each of these factors for all the activities. Here, in the given example, we have 5 activities from A to E. Now, obviously, there is some formulation. Let's go one by one. In order to know the theoretical exercise, we must know what is the labor hour per production operation, what is the target rate, number of working days per week, and the length of working day. Once you calculate gang size, then we round gang size into a multiple of 3. Now, this is 3 is the word that I've seen. I'm not sure what is the basis of 3, but it's generally when you calculate actual gang size, we choose multiple of 3. So you can say it's a part of formulation. Then the actual rate of output, you have to multiply the actual gang size into number of days per week multiplied by the length of the working day, that is an hour per activity. Then the time in days of one activity is the labor hour per operation, optimum number of operations per activity, and the length of working day. Time from start of one unit to last unit is the number of working days per week multiplied by total units divided by actual rate of output. Total divided by, now this, I'm sorry about this appearance of the formula slide. It's the total unit minus 1. This is n minus 1, as this n minus, is very common when we not want to know between how to calculate the middle values between first unit and the last unit. In our case, this is total unit is 6 minus 1 is 5. Now, our formulation continues. For the start of Unit 1, for first activity, this is always 0. For all other activities, is the end day of the previous activity. It's just like CPM, a very common method in highway construction. Then the last day for Unit 1 is, for first activity, it's the time in days of one activity of that activity that has been calculated in the formulation. And for all other activities, start date of Unit 1 is to be added with buffer allowance for that activity that is in question. So, to know the last day for Unit 1. Once these two are calculated, then the third is the start of last unit. Now, for the first activity is the time from start of one unit to the start of last unit. The time from start of one unit is already calculated, the formulation. For all subsequent activities, start day of unit 1 plus time from start of one unit to start of last unit of that activity. Finish last unit is, for first activity, is the start of last unit plus time in days of one activity of that activity. For all subsequent activities, start of last unit plus time in days of one activity of that activity. I think this may be a little boring for you, but I can understand and you can understand that you can use this formula. This formula is very universal and you can apply it everywhere. That's why I'm giving you formulas before solving the example, and we'll keep on repeating this formula so that the actual explanation could be understood. Now let's come to this problem. For the detailed calculations, we need to calculate the theoretical size. Now, people, we know that gang means group of people assembled together for the execution of the task of work. In this case, this is the clearing and grubbing. One thing it should be noted here, that it's not only the people that are working, but the people who are working with machine as well. Obviously, this discussion may go beyond the scope of this project, so let's not get confused with these statement like labor required and like that for this LOB problem. Now, the theoretical gang size is the labor hour per operation multiplied into target rate into the number of working day per week into length of the working day. Now, we start with our first activity A, clearing and grubbing. Labor per operation was given to us 110. The target rate is 1 kilometer per week. Number of working days is 5, and the length of working day is 8. So that's how we come up with this 2.75. Similarly, for earth moving, now the only thing that has been changed is this labor hour per operation. Otherwise, all those values are same. Then activity C, again this 280 has changed and the have remained constant. Base, again this is 50, and then the rest is same as of all other activity, and activity is asphalt paving. This is 40. I could have used Excel sheet, but I feel if they have all the formulation is being very clear. Just if you're a beginner, you can easily understand this formulation rather going to the Excel You can go to Excel anyway. We adopt Excel anyhow. But here I have shown the detailed calculation that is very needed. If you have error, you can always find this here. So now our first task, calculation of theoretical gang size for all activity has been completed. Now let's go to our second task, that is actual gang size. And I said we have what we need to do is we have to round our theoretical gang size into multiple of given rate of 3. So for for activity A, we have calculated 2.75. So next multiple is 3. That's why I've taken this value as 3. Earth moving, it was 8. So next multiple of 8 will be 9. 3 is 9. Subbase 7 we have taken as 9. And for activity D, it was 1.25. So we have taken 3. And asphalt paving, as already shown to you, is again taken as 3. So whatever we have done, we can see we have round these values up to next multiple of 3. So this is our second calculation, that is the calculation of actual gang size, or what we call a practical gang size, we can say. Now, the third step is we need to know the rate of output. The formula is given here, and let's see how it is being applied. Clearing, grabbing. So for the first thing, actual gang size we have calculated in the previous step. This number of working days and length of working days is a constant, and hour per activity, labor hour per day, that was also given, and we have used in item number 1 of this calculation. Similarly, we have for earth moving activity, now you can see that only 3 has been changed, and obviously 9 and 320 has been changed. This is actual gang size was 9 for activity B. For activity C, again the actual gang size is 9, but the only variable here is 280. Then base rate of, again, now this had we calculated 3. This is constant, and this is again given. And for asphalt paving, again, so we have calculated this actual rate of output as 1.09, 1.139, 1.29, 2.4, and 3.00 respectively. Now, let's move on. Now we need to know how much time one activity will be need in days. So clearing and rubbing, the formulation is again optimum number of operations per activity has been used, and the length of working day. So this again has been calculated for each of the activity. For all of these, all of the PowerPoint, the PDF form of this presentation, the link for downloading the pair is present in the comment section. So you can download a presentation in case you are missing out something, or you can want to recheck what I have calculated. So this link will be made available to you at the end of this presentation or in the comment section. We come up with the next thing, that is the time of start of one unit, the duration of the time between the last unit and the first unit. So that's number of working days, total unit, that is total unit minus 1, and then actual rate of output. First activity, so number of working days, we know that 5 per week, and we have total of 6 kilometers that is to be constructed. 1.09 we have already calculated, so this comes out to be 22.9, And I have this thing that I always tend to make this time in terms of duration, not in terms of hours. I take it rounded to number of days because this is a construction activity. You cannot, you may have 22.9, but on it's not a pure mathematical constant that this has to be in this way. This should be rounded off to the next practical value. Earth moving, now that will need 23 days. There will the gap between the first unit and last unit for earth moving is 23. For subbase, it is 20. For base, 11. And for asphalt paving, it is 9. So this is how you can see the only variable is the denominator that we have calculated earlier. So that's one of the thing with this LOB is that we have to go step by step. We cannot do it randomly. Each step is followed to be a next step. Now, another thing, most important thing, that is the main data that is being needed to draw the graph is this calculation of the start time, start time for the last unit and the finish time for the last activity or last unit. So we have to calculate activity per activity. So let's start with activity A. Activity A is very simple. You can see here. Now for the time of start of one unit to start of last unit, start day for unit 1 is for first activity it is 0. Therefore start time for A is 0. Last time is first activity time in days of one activity of that activity, and that is 5. Start of last unit, time from one unit to start of last unit, that has also been calculated previously. So it's just 23. And finish last time is simply you have to add 5 plus 23, that comes 28. So you see, this is a very sequential manner. In the activity is a very simple start time. It's always 0. You have already calculated one unit activity, that is 5. You already know the time between first activity and the last activity is 23. And we will add these two columns, these two values, we can get the time finish for the last unit. So that's, calculating for activity A is very simple in nature, in this method, I could say. Now, let's move on to the second activity. Now, here there is some formulation. So, start day of unit 1, and we say that for all other activities, this is a formulation end day for unit 1 plus previous activity plus buffer allowance. So, for activity B, we can say this is the end day for unit 1 of activity A plus buffer allowance for activity B that was given to us, and that was 5. So here we have this value that the last unit, the start day for the unit 1, end day for activity A, as we have calculated here. Let's go back if you have some completion. So end day for last day for unit 1 was 5. So we have 5 here. And then the buffer activity is 5. That is why it is 10. Let's move on. And now we have to also have a check that this activity, any time of activity B should not come before the activity A. So this is what we need to check the constraints, because you cannot logically start earth moving without clearing grubbing. So if by somehow because of your data or because of some error, you find that your start day for unit 1 for activity B is before the start day of for uh, unit 1 of first activity, then we have to do some correction technique that obviously also is a part of this example. We will show you how. But first you have to check with that whatever value of times that you are calculating for the next activity, that should be greater than the, the corresponding time of the previous activity. So that's why this check is being made here. Obviously, it is okay. There was 10 and there was 0 and we have 10 here. Then uh, the so that for all of for activity B, start day of unit 1 of A plus unit time of activity B. And so that why, so whatever is that, this is start time 10 is what we have calculated, and now we have added 5 for this time. So that's become 15. Again, it's greater than A. We move on. The third time, the start of last unit, and the formulation start of unit 1 plus time from start of 1 unit to start of last unit of activity B. And we have already calculated that last unit as 10. The first start day of unit 10, one was 10, and the time we have calculated for the formulations, that was 23. That's why start of last unit for activity B is 33. Again, if you check with the corresponding value, it is good, it's okay. Now, the last time for activity B is calculated at the start of last unit plus time in days. So whatever 33 we have to add with 5, that we have calculated time in days for one activity. So that's why 38 is the last value. Now, again, we move on to the third activity. Obviously, that's great. A is greater than A. Now, for activity C, again, we are dependent on activity B plus buffer allowance for activity C. Incidentally, in the given data, the minimum buffer allowance is same. So that's why you just keep on adding 5 in for calculating start date for unit 1. So that's 20. And now 20, the second last day, this 20 has to be added with the 4 that has been, we already calculated the formulation. So that's why it becomes 24. Again, the corresponding values of B is less than 20, and the last day for activity B is less than 24, so it's okay. Then we know that the first time is 20, and then we have calculated this 20, the time between start of one unit to last unit. So that's become 40. Again, we have checked with the corresponding time of activity B, it's okay. And then obviously the thing 40 is to be added with 4, so becomes 44. Again, you have to apply that check. So let's move on to activity D. Space. Now, same thing. 24 plus 5, 29. Need to check. It's okay. Just an error. This is activity D actually. sorry. Then last day is again, this is 29. We have calculated. Then unit time 231. So that's okay. Continue. Again, the same formulation. 29 plus 11, 40. Oh, this is not okay. Actually, this time matches the time with activity C. And this is where there is a problem. So let's move on and we see how this problem is solved. We finish last unit. Start time. That's we have to add 40 plus 2. That's become 42. Now, what's happening? Again, this activity time is before the activity time for D that is been calculated is before the activity time of last unit of activity C, and which is not possible. So that we can say, since all times of activity has to be revised, since no time of forward activity be less than back method. So how we do it is I'm afraid that is, the formula is sometimes something different. The starting with data is different. So let's see. So we are taking this as activity D asterisk because it is being revised. The error has been pointed out. Now we start with first calculating last unit for activity D. So what we do is for revised activity, first time of last unit of activity C plus buffer allowance for activity D. So it becomes 49. Obviously, now it becomes more. Then we go back the first calculation, that's time from start, and simply first day for activity of last unit time minus time from start of one unit. So 49 minus 11 becomes 38. Now we are now right on the course. Obviously, now we are going to calculate times 7, 8, 7, and 9 from this data. So when we revise, we calculate the serial number 8 first, and then we go back uh, with 6. And obviously, those techniques are different from what we were doing if our activities were normal. So again, now 7 and 9 are now very simple now. Again, that's 38 plus 240. Now it's okay. And then for all subsequent it's 51. Now it's okay. So that's how we have calculated D asterisk. Now that comes to the activity E, asphalt paving. Time from start of one unit to start of last unit. Again, we have gone with the same procedure. 40 plus 5, 45. It's okay with the revised activity of D. Then it becomes 45 plus 2, 47. It's simply it's what we have done in calculators of BAC. So again, I'm going fast because I know this is very trivial. Again, we have to check. We need to apply a check. It does mean that if you have applied correction for one activity, the next activity may not need any correction. So we need to be checking each time the deliberation I have made. Start again. This becomes 54. Again, it is less greater than the corresponding activity of D. Finish last time. And this becomes 56. So in summary, if we summarize this table, we can go with these values. This is the summarizing the results, what formulation we have done. We can use it in Excel sheet, or you can, while calculating or rechecking the calculations, you can always take this printout first and then you can do it like this. So this is what we have summarized, and this is the time values. And again, you see each of the uh, next time is greater than the previous time. For instance, 20, 38 is greater than 28. And here, the problem was here. Here, when we were calculating D, the actual time, we were okay with this, the first unit uh, start day and the last day, but we had a problem with this here, that the start day of unit C and start day of last unit of C, D was similar, and this may be tolerated, but this cannot be. You cannot finish uh, A, C, D before C, because they are interrelated, and that's why we have correction. And then when we had a correction again, we know that each of these values, calculation D aesthetic is greater than D. So that's okay. And obviously, we did not need to devise E for the situation as shown. Each of the values are greater than the corresponding values of the activities. I just keep on repeating because this is the error that is being oversighted while calculating, while doing these detailed calculations. Now, so last but not least, as we can see, and you can see it's strange that as we compare to activity D and activity E, activity A, B, and C are slightly slower. So actually, when I was discussing the LOB, I've shown otherwise, but this is, you can see that it can be realistic, that it can be happen that the activity D and E are much more faster, the rate, the completion time activity D are more faster and than the completion time of activity A, B, and C. And um, if you are the student, if you are, the worker, while doing the highway project, sometimes clearing and graving and earth moving, they need much time than the asphalt paving. So whatever the result shows, they are very practical results. So with this, I thank you all for listening me, and I always at the end of the time says that uh, please subscribe me so that I become um, more motivated. And I'm thinking of the Hindi version of this problem as well. So till then, bye and take care.